All right. So we saw that the electric field for a static electric field, and you can see that there's no time information in there. And the static electric field is created by a distribution of charges. A static electric field can be written as the gradient of an electric potential. Okay? And what this gradient tells you is the direction in which the electric potential is increasing. This is a scalar function, okay? Meaning it's associating a number with every point. This is a scalar valued function. And the gradient operator tells you the gradient operator is a vector. This is a vector. The gradient of a scalar field is a vector. It tells you at any given point in what direction is the electric potential increasing the fastest, and it gives you the rate of increase. And the negative sign tells you that the electric field is pointing in the opposite direction. Okay, so if the electric field, if the potential is increasing in this direction, electric fields are pointing in that direction. Okay, so here's a differential form of that equation. This is an integral form of that equation. Okay, if this is true, then if you take the line integral of this electric field from any given point to that, that'll give you the difference in electric potential. Okay, so these two equations are equivalent. This is in English, this is in Spanish. Okay. All right, so again, one is a differential equation form. Differential equation form gives you local information. And integral equation gives you more global information. Okay, so it's telling you how two far away points are related, and this is telling you some local information. Yep. All right, you have a question?
Yeah. So you said like gradients are you usually learn at calculus 3. You said correct?
Right.
Okay, I was just curious.
Mm-hmm. Well, but I've mentioned it at least 5 times here in this class between physics 1 and 2.
That's true. I did pay attention.
You need to learn to pay a little more attention. See, that comment was looking for an excuse to get out of learning. Anyway, all right, so this is, you saw how electric fields and electric potentials are related, okay? So if the potential is increasing in this direction, electric field is pointing in that direction. Electric fields point in the direction of decreasing potential. Okay, so in this example, what this is showing you is, this equation is showing you is, so here's a constant electric field. All right, how do you make a constant electric field, for instance, in this room? If you wanted to make a constant electric field here, again, we'll learn about this in the next chapter. You smear that wall with positive charges, this with negative charges, and you get a constant electric field like that, okay? So if you have a constant electric field like this, okay, so doing this line integral and going from here to there, this is just E dot ds. E is constant, that comes out, and then it's just adding all those vectors, so it will be E dot s vector. Okay, and if E and s vector are pointing in the same direction, this guy is positive, so this quantity is negative. That means Vf is smaller than Vi. And that's what we have been saying, that the electric potential here is lower than the electric potential here. Electric fields point in the direction of decreasing potential. Gradients point in the direction of increasing potential, and electric fields point in the opposite direction. Electric fields point in the direction of decreasing potential. Okay, so you can just memorize this formula. The change in potential between 2 points for a constant electric field is just E dot ds. And if you're pointing in the direction of the if you're going along the field lines, delta V, change in potential between 2 points, is just ES, okay? And the minus sign. As long as you don't have to even put the minus sign, as long as you remember that the potential decreases. Okay, if we can use the minus sign. It's the potential difference between 2 points is just E times S, okay, as long as you're going in the direction of the potential. So electric fields point in the direction of decreasing potential. All right, here's a very, very important unit that you will run across many times. Yeah. So let me do another diagram here. Here's an electric field. If you remember, the force on a charge in the presence of an electric field is given by this formula. Okay. So what does this formula tell you? If the charge is positive, the force is in the same direction as the electric field. If the charge is negative, the force is in the opposite direction of the electric field. Okay. Now, in a gravitational field, for instance, here, I drop this object. What happens? This object fell along the direction of the gravitational field. And what was happening? Potential energy, gravitational potential energy was being converted to kinetic energy. It was gaining speed. Okay. In one of the previous formulas, you'll see that change in potential between 2 points is the change in potential energy divided by the charge. That's how this thing is defined. So change in potential energy is equal to Q times change in potential. Okay, the amount by which potential energy changes for a charge falling through this potential difference is given by that. All right, now let's come back to this. In this diagram, where is the electric potential high? Okay, so V, it's high here, it's low there. Okay. All right, so you saw that electric fields point in the direction of decreasing potential. Okay, now if I put a positive charge here, which way will it fall? Down. It'll fall in the direction of the electric field. If I put a negative charge here, it'll fall in that direction. Okay, so when it falls, it's losing potential energy and gaining kinetic energy. And when this is falling in that direction, it's losing potential energy and gaining kinetic energy. Okay, how much potential energy does it lose? It loses the charge times the potential difference. What is the charge of an electron? 1e. What is the charge of a proton? 1e. The charge of the proton is the same as the charge of the electron. Okay? So let's say there's a 1 volt difference between these 2 points. A proton will fall there and it will lose that much potential energy, 1e. E times 1 volt. And if an electron falls through this 1 volt, the electron falls in that direction, it also loses 1 eV. Okay, and that's how much kinetic energy it gains. So this is a unit of energy. Okay, when a charge of 1 E falls through 1 volt, that's the potential energy it loses. Okay, so 1 eV is a unit of unit of energy, and the charge, and that's equal to 1.6 times 10 to the minus 19 joules. Okay. And this is a very useful unit. So that's the energy, kinetic energy an electron would gain in falling through 1 volt, or that's the kinetic energy a proton would gain in falling through 1 volt. Okay. Now, if you're doing any chemistry, the reaction energies involved in a single reaction, let's say H2 combining with oxygen, are of the order of electron volts. So, for instance, when you burn carbon, okay, somebody chat GPT that? Okay, I believe somebody chat GPT that? Ask chat GPT this question. Okay, so it releases about 4 electron volts of energy. Okay. If you mess with the nucleus, which we learned about, okay, you gain about 200 MeV of energy. All right, so what we're saying here is the following. All of chemistry is in electron volt range. Okay? And if you're doing nuclear physics, you're in million electron volt range. Okay? The energies involved are 1,000,000 times more. So when you're messing with the nucleus. In a particle reactor, in a particle accelerator, you're going to tera electron volt range. That's a trillion electron volt range. So that's the energy, kind of energies involved. Okay. Do you guys know why you go to such energies? All right, so a particle accelerator is really is a microscope. Here's what I mean by that. Okay, so when you do quantum mechanics, well, okay, so if you want to see anything, so how do I see this guy? How do I see this guy?
The light reflects off of it.
Yeah, a light beam falls on it. I look at the light, reflected light. Okay, so the light is the probe to see that. Okay, so if I use this probe to see something, the smallest thing I can see is this, of the order of the wavelength. Okay, so if I wanted to see this thing with this probe, I can't see that. Okay. So to see this probe, what do I need? I need a shorter wavelength. Okay, so for instance, if you want to see an atom, you need X-rays. Okay, and if you want to see a cell, visible light is good enough. Okay, so a cell is obviously smaller than the a cell is bigger than this wavelength of visible light. What if I want to see inside a proton? Okay, so here's an atom. This is 10 to the minus 10 meters. So I can use X-rays. What if I want to see inside a nucleus? This is 10 to the minus 15 meters.
Gamma rays?
Yeah. So except that focusing gamma rays and all is very hard. What if I want to see inside a proton? What if I want to see, I want to mess with quarks? Okay, so here's where it comes in. Okay. So when a particle moves, there's a wavelength associated with it. Okay. And the wavelength is okay, so see, this is the mass of the particle, this is the velocity of the particle, and this is the wavelength associated with it. What is this equation saying? The faster the particle is going, the shorter the wavelength, the more finely you can probe things. Okay, so you want to look inside a proton. You see? Hello there? See? That was a big story that you missed. You were not. The faster a particle is traveling, the smaller its wavelength, the finer details you can probe. So an accelerator is really a big microscope. Okay. All right, so again, so the Large Hadron Collider at CERN, it's, so the energy of the particles are 10 to the power of 13 electron volts. Okay. And what this is saying is the mass of a proton is 1 GeV, which is 10 to the 9 electron volts. Okay, so that means in the Large Hadron Collider, proton beams go in opposite direction and collide, and these protons have energies 10,000 times their mass. See, that's 10,000 times their mass. So they're 10,000 times heavier. That's how fast they're sped up. Okay, and so the associated wavelength is very small, and you're probing deep inside the structure of matter. All right, so here's an equipotential surface, a surface where the potential is the same everywhere. Okay, 9 volts, 8 volts. We saw that electric fields point in the direction of decreasing potential. Okay, and at any given point, electric field is perpendicular to that surface. Okay, so let's say, here is an equipotential surface. Okay, at this point, the electric field is pointing in this direction. At this point, the electric field is pointing in this direction. So electric fields point in the direction of decreasing potential, and they're perpendicular to equipotential surfaces. All right, so here are two charges, two positive charges. These are equipotential surfaces. Okay, and so from a positive charge, electric fields point away in that direction. So now you can surmise that potential is higher here, lower here. Okay, so electric field is perpendicular to that. This is a dipole, and the electric field from a dipole. So these are equipotential surfaces, and the electric field is pointing like that. Okay, this is what we'll do in today's lab. We will plot this electric field, okay, around a dipole. Okay, so if you wanted to measure the electric field at this point, what you do is you measure the potential you find 2 points. If this is equipotential surface, then the potential difference between these 2 points will be 0. And then you know that the electric field is perpendicular to that point. Okay? So we'll use that fact. We will map this electric field. All right. Where do you encounter a dipole?
Water.
Water molecule has a dipole moment. Okay, so oxygen is greedy for electrons, so it has a dipole moment. Whenever you hear of molecules that have polar heads, when they say polar heads, what they mean is that portion of the molecule has a dipole moment. Okay, and this is very useful. Okay. So you saw that the bilipid layer, the cell wall is a bilipid layer. And why did this layer form like that? The polar head is attracted to the water, so there's water outside and water inside. And this is the lowest energy configuration. Okay. So again, without these kinds of dipole moments in the molecule, you couldn't form an enclosure. You couldn't form life. Okay. All right, again, so we will do that. Okay, so what we have said now is the following. So let's say okay, so I give you these numbers. Let's say At this point, it's 9 volts, 9 volts, 8 volts, 8 volts. Which way is the electric field pointing? Yeah, so the electric fields are pointing in this direction. Okay. Now, what we want to do is the following. Let's say there's a positive charge. I want to know what is the potential at all these points around a point charge. Okay, so that's the formula we'll give you. And the potential at a distance r is, the electric potential is K, the Coulomb's constant, times the charge divided by r. If the charge is positive, the potential here is positive. If the charge is negative, the potential here is negative. Okay, and as you go further, if the charge is negative, this is negative, but here it's a smaller negative number, so the potential is increasing in that direction. And if it's a positive charge, the potential is decreasing in that direction. Okay, so this is the formula for the potential from a point charge. Okay, and that's what we're going to derive. I'm actually, all right, how many of you guys have done spherical polar coordinates, cylindrical coordinates, and have you done?
Some coordinates, but not a lot.
The Calc 2 classes should have gotten into polar coordinates yet.
What, are you in Calc 3?
Yeah, I'm in Calc 3, but most of the people here are in Calc 2.
All right, it doesn't matter. I'll give you a little preview of it. All right. So again, this is the formula that we want to derive that I gave you. Okay. So the potential from a point charge is the Coulomb's constant times the charge divided by R. Okay. All right, so that's the formula we want to derive. So here is the relationship between, the integral relationship between potential difference, and electric fields. Okay, so you have to do this line integral. And what is this equation telling you, among other things? How do we get from A to B? What path do we take? So this equation is telling you, see, this answer is independent of the path you took. So in evaluating this integral, you could take one of billion paths, or one of infinitely many paths. And if you like country music, what path are you going to choose? The hardest path. A very good answer. And if you don't like country music, if you like jazz music, you choose the easiest path. All right, so again, the value of this line integral is path independent. Okay, so let's evaluate this integral. Okay, so the reason you learn all these different spherical coordinates, different coordinate system is, okay, doing this integral would be very hard in Cartesian coordinates. It depends on the symmetry of the problem. See, the electric field from a point charge is radially outwards, okay? And so the electric field is given by KQ over R square, R hat. R hat is a unit vector in spherical polar coordinates. And let me, so here are spherical polar coordinates. Yeah. And by the way, what you learn in math and physics, physicists and mathematicians use slightly different notation. All right. So here's a point, and you can, of course, give its coordinates in Cartesian coordinate system, or you can give it in spherical polar coordinates. Here is the distance r. Okay, here is the projection of this point on the xy plane. This guy is called phi. That's what the physicists do, and this angle is called theta. So the coordinates of this point, so the address of this point can be given by these three numbers or can be given by these three numbers. Okay? Which three numbers have more information? Huh?
The same.
They have the same amount of information. Okay, so you should be able to translate from one coordinate system to another. So for instance, z is r cosine theta, and x is, so z coordinate is r cosine theta, r sine theta is this guy, and then, so x would be, so this is r sine theta cosine phi, x is r sine theta cosine phi, and y equal to r sine theta sine phi. Okay, anyway, those guys are related. Okay, don't worry about that. Okay, so just like I, j, k are unit vectors along these directions, here is r hat is a unit vector along the radial direction, and if you draw a circle in that plane, this is phi hat, that's a unit vector along this direction, and that's theta hat. All right, so a small displacement dr in Cartesian coordinates can be written as dxi dyj dzk. If you wanted to write the same displacement in spherical polar coordinates, you would write it as dr r hat. So that's the distance parallel to that. And then distance parallel to this vector would be r sine theta d phi phi hat, and then a distance parallel to this would be r d theta theta hat. Okay, so I generally I would write this second and that third. Okay, so again, this is an infinitesimal displacement. This is parallel to the x-axis, parallel to the y-axis, parallel to the z-axis. This is parallel to the r hat axis. This is parallel to the phi hat axis, and this is parallel to the theta axis. Okay. Again, it's the same displacement. This is in English, this is in Spanish. It's just a different language. Why do we use different languages? I mean, if you're in Chile, you don't want to be talking English. You want to be talking, Portuguese or Spanish. This is more convenient. So what we are saying is, if you're doing this line integral, you don't want to do it in Cartesian coordinate. You want to do it in spherical polar coordinates. Okay, I'll show this to you in a second. So VB minus VA equal to minus, so A to B. Electric field is KQ over R square R hat ds. Now that integral, the small displacement we take in right in polar coordinates, R d theta theta hat plus R sine theta d phi hat. And when you take this dot product, see only this survives. R hat is perpendicular to theta hat, so that dot product will be 0. R hat is perpendicular to phi hat, that dot product will be 0. Okay. So only this one survives, k phi r square dr. And now this integral is easy to do. Even I can do this. And that's equal to kq by r. Okay? And initial to final point, or A to B. So this is kq rb minus kq ra. So the potential is KQ over R. All right, so again, it's all those coordinates, you learn about them because, when you're doing calculations for problems, depending, if a problem has spherical symmetry, then you use spherical polar coordinates. If a problem has cylindrical symmetry, then you use cylindrical polar coordinates. Okay? And if it's appropriate to, so if something is in a square or a rectangle, then you use Cartesian coordinate system. All right, so the potential of a point charge is KQ over R. So if the charge is positive, the potential is positive, and so on. Okay, so let's say you have a bunch of charges. If you wanted to find the potential at this point, you find the potential due to this guy plus the potential due to this guy. The potential at any given point is just a number. So you find the potential due to this guy, potential due to this guy, and then add up all the numbers. That's what this is. K, QI over Ri. Look at this. What this is telling you is, so for this charge distribution, what are they telling you by this guy, this contour? What is that contour telling you?
So line equal left.
Yeah, everywhere on that surface, the potential is 350 volts. That's what they're telling you. Okay? So what do you call that surface? An equipotential surface. Okay? Now, why did we do that? Now, let's say if this was an equipotential surface with potential equal to 340 volts, then you know that the electric field is pointing in that direction. Okay? That's why you want to know that kind of stuff. Okay? So this is the electric potential of a dipole. Here's the positive charge. Here's the negative charge. This is how the potential looks like around a dipole. Yeah. A dipole, again, is a positive and a negative equal charges separated. And at that point, at distances where this distance is large compared to this distance, the potential is given by this. Okay. So for a point charge, the electric potential falls off as 1 over R. From a dipole, the electric potential falls off as 1 over R squared. It falls off faster. Okay. If you wanted to calculate the electric potential due to a thundercloud, what you do is you break this thundercloud into little pieces. Here's a point charge. The electric potential due to this point charge over there is K dq divided by R. And then to find the total potential due to the thundercloud, you sum over all those little pieces, and that's an integral. And this will be a three-dimensional integral. And of course, you will only be able to do it for very symmetric cases. Okay. What this is saying, again, this is the fundamental relationship between electric potential and electric fields. And when is this true? Is this true for what kind of electric fields is it true? Huh?
Static.
Very good. Okay. For static electric fields. If it's a time-dependent electric field, so for instance, for your cell phone signal, which is time-dependent, that's this one. Yeah. All right. So if you put a bunch of charges on a conductor, you saw that the charges reside on the surface of a conductor, and the electric field is perpendicular to the surface. Okay, so what this is saying is, okay, so if the electric field is perpendicular to the surface, let's take a path along the surface. The electric field dotted with this displacement, what will that be? E dot ds, this is 0. So if you take the line integral along that path, that will be 0. So what that means is the potential at point B is equal to the potential at point A. So a conducting surface is an equipotential surface. So if I go to a store and buy charges and throw some charges on this faucet, all the charges would reside on the surface, and that is an equipotential surface. In fact, what is the electric field inside the conductor? 0. So if you do a line integral along here, that would be 0 as well. So the potential here is the same as the potential on the surface. So in fact, the entire conductor is an equipotential object. Okay. So if anywhere on the conductor, if the voltage is 10 volts, that means everywhere on the conductor, the voltage is 10 volts. Okay. So here is a conductor. You put a bunch of charges, they reside on the surface, and you see everywhere on the conductor, the potential is constant. Okay. If you're outside the conductor, this is spherical conductor, this is acting like a point charge, and the potential is falling off as that. The electric field is 0. The electric field is, remember, the electric field is negative of the gradient, is a derivative of the potential. The derivative of 1 over r is 1 over r squared, minus 1 over r squared, okay? Okay, so here's an interesting thing, okay? Again, in the next chapter we'll learn. Here is one way of creating a uniform electric field. Smear this wall with positive charges, negative charges, and you have a uniform electric field. Now, if you have a uniform electric field and you go to a store and buy a piece of metal and bring the piece of metal in here, put the piece of metal here. Well, what does the metal want to do? It wants to make the electric field inside go to 0. And it makes the electric field go to 0 in 10 to the minus 18 seconds. Very fast. And how does it do that? See, it rearranges charges like this. And you see the field, electric field also got altered. So here, well, why do we care about that? Sharks detect stuff that come around them. So they produce an electric field. And if there is some object with metal around, do you have metal in you? Yes, you do. Hemoglobin has iron. All right. So you would alter the electric field around it. Right. But anyway, so here you see this electric field got altered by this piece of metal. We talked about a Faraday's cage. So here's the metal cage. What kind of electric field are you scared of? What kind of electric field should you be scared of? What causes lightning? 3 million volt per meter. David, I told you never to forget it. What's happening, my friend? Okay, so 3 million volt per meter. Okay, what happens at that electric field? Very good. At these high fields, okay, here is air that is insulating. And if you have a stray electron, which you always do, if you have an electric field like this guy will accelerate and it'll start knocking off electrons before it gets fast enough to start knocking off electrons from these molecules. And now the air has become conducting. And if there's a thundercloud here, if this is conducting, it's like connecting a wire through the atmosphere, through your body to the ground. And that's not good for you. All right? 500,000 amperes passing through is not a very good feeling. Yeah. All right, anyway. So you have strong electric fields here. And if you're in a metal cage, the charges here rearrange such that they will produce a counter electric field which will cancel this electric field and make the net electric field inside here 0. So you can have lightning outside all day long, and inside you'll be totally protected. That's a Faraday's cage. Okay.
So the air mechanism work that way?
I'm sorry?
The air mechanism work that way?
Yep. Inside you're protected. I don't know if, yeah. Any metal cage. Any good conductor. And the reason it's able to respond that fast is because the electrons are so light. You tell them something and they'll do it immediately. All right, so here is a Faraday's cage. You see there's a non-zero electric field outside which is lining up these metal particles, and this is zero. Yeah. All right, so here's a integral equation, and from this integral equation we'll derive this differential equation. Okay, so again, differential equations are statements about very local phenomena. What this is saying is at the derivative at this location is equal to that. And to find a derivative, all you need to know is two neighboring points, close by points. This is a statement about two faraway points. Okay. All right, well, it's a statement about any 2 points. It's a statement about faraway points, but it's also a good statement about two close by points. So take two infinitesimally close points, and the potential difference is an infinitesimal potential difference, and that's just that. There's no summation needed because that's a small distance. Okay? So that's equal to that. And when you do multivariate calculus, so change in a multivariate function, so this, what this is saying is the change in this multivariate function is equal to, so this is where you learn partial derivatives. It's the change in v when you move parallel to x, okay? And dx plus the change in v due to y plus the change in v when you move parallel to z. Okay? So this change is equal to the change because of motion along the x-axis, this change due to the motion along the y-axis, and this change due to the motion along the z-axis. So let's say if you went from here to there, x-axis, y-axis, z-axis, okay? So that's what this is. And the dot product of these two guys is that. So you can equate that to that. Ex is del v by del x. Ey is del v by del y. Ez is negative del v by del z. Okay, so that tells you that the electric field vector is equal to the negative of the gradient. Okay, so what we have shown is we've shown you that this statement and this statement are equivalent. Okay. All right, so electric fields and potentials, these are equipotential surfaces, the blue dotted lines, and electric fields are perpendicular to that. See, all these are equipotential surfaces around a point charge. Those are equipotential surfaces, and that's a field line. Which way does the field line point? It points at any location. It's perpendicular to an equipotential surface, and it points in the direction of? Very good. Decreasing electric potential. Okay. Again, we will plot this field due to a dipole. All right, if I have two positive charges, what is it that they are doing? They are repelling each other. If you compress a spring, what is the spring wanting to do? Decompress. If you have a spring compressed, you have energy stored in it, potential energy. Okay, so just like that, if you have two charges like this, there's a potential energy stored in it. Okay, and the potential energy is that much. K, Q1, Q2. What if you have a positive and a negative charge? What do they want to do? They want to attract each other, so it's like a stretch spring. That has potential energy as well, okay? All right, so there's the potential energy. Yeah. And K is the Coulomb constant. If the charges are opposite, the potential energy is negative, and if the charges are like, then the potential energy is positive. Anyway, so there's potential energies stored in this thing, okay? So if you have a constellation of charges, the potential energy is due to this pair plus this pair plus this pair, okay? That's the total potential energy. You saw that to remove smoke particles, you have an electrostatic precipitator. We've talked about this before. You apply potentials of up to 100,000 volts. Okay, so here's wires, here's metal plates. The metal plates are positively charged, the wires are negatively charged. And if you apply 100,000 volts, this guy will spit out electrons. This wire will spit out electrons. And if you pass this smoky air through it, these smoke particles will attract these electrons, become negatively charged, and then be attracted to the positive plates. And you can remove 99.9% of these particles. Okay? And then every once in a while, you shake these guys and drop that dirt. The price you pay is about 2 to 4% of the power plant's electricity. Okay? So you guys will be driving these things in the future. Okay? So when you pump gas, what is it that you're doing?
Burn the gas.
When you pump gas, you're buying energy. When you charge a battery, you're storing energy in the battery. Okay. So go check out prices for electric vehicles. The price depends on the size of the battery, essentially, all other things being equal. Okay, so this is the size of the gas tank, essentially. Right now, electric vehicles, you've heard the description, they're batteries with 4 wheels. That's what electric vehicles are. Yeah. So this is the cheapest Tesla model, the smallest, and 85 kilowatt hour is the biggest, I think, something like that, okay, for the cars. Yeah. All right, so what this problem is saying is, so kilowatt hour, yeah, by the way, if you look at your electricity bill, you are paying by kilowatt hour. This is the unit of energy, and this is equal to 3.6 million joules, and you pay about 12 cents for this guy. Okay, so when you charge this battery completely, 50 times that is 100 times that, you're storing about $6 worth of electricity in that. Okay. All right, if you use up 60% of that, you get 114 megajoules of energy. That's what that is saying. In a gasoline, this is a 50-liter gasoline. Each liter has that many megajoules. If you burn that much gasoline, you get 1,700 megajoules of energy, of heat. 100 megajoules versus 1,700 megajoules. So that's what they're up against. But heat is only 30% efficient. You can only convert about 20% of that into motion. Whereas electricity, you can convert 90% of that into motion. Okay. So, eventually the density will increase and all that stuff. You will be able to store more energy in batteries, and anyway, they'll replace it. But what is the biggest thing about electric cars? Why will you all be driving electric cars? What is the biggest thing?
Gasoline is finite.
Yeah.
Lack of carbon emissions.
I'm sorry?
Electric vehicles don't create as much.
So the operational, so here the operational carbon footprint is 0. What does that mean? When you burn gasoline, you're emitting carbon dioxide. If you're charging your car with solar and wind and then driving the car, you're never dumping any CO2 to drive a car. Okay? So that is the key. So, okay. And okay, so again, in 100 years, you want to have a lifestyle where you're dumping no CO2 in the atmosphere. Okay, so 10 to 15% of it is in transportation, and so you will remove that.